Good morning, depending on your location, from the U.S. Fish and Wildlife Service's National Conservation Training Center in Shepherdstown, West Virginia. My name is Ashley Fortune Isham, and I would like to welcome you to our webinar series held in partnership with the U.S. Geological Survey's National Climate Change and Wildlife Science Center, or NISQWIS, located in Reston, Virginia. The NISQWIS Climate Change Science and Management webinar series highlights their sponsored science projects related to climate change impacts and adaptation and aims to increase awareness and inform participants like you about potential and predicted climate change impacts on fish and wildlife. I would like to welcome Abby Lynch, who is a research fish biologist with NISQWIS, to introduce today's speakers. Abby?
Hi, thanks. It's my pleasure to introduce today's two speakers. First, we have Dr. Gabriel Sinai, who is a research physical scientist with the U.S. Geological Survey's Earth Resources Observation Science Center. Sinai is co-located with the North Central Climate Science Center in Fort Collins, Colorado, and is a faculty affiliate with the Ecosystem Science and Sustainability Department at Colorado State University. He conducts applied research on water use and availability assessment and drought monitoring using satellite-derived data and hydrologic modeling. Our second speaker for the day is Dr. Imtiaz Rangwala, who is a research scientist at the Cooperative Institute for Research in Environmental Sciences at the University of Colorado Boulder and NOAA's Physical Sciences Division, who leads the Climate Foundational Science Area of DOI's North Central Climate Science Center. He is a climate scientist with training in assessing and diagnosing regional scale climate change. Using climate observations and models, he works to understand and quantify climate processes relevant to regional warming trends and hydrological processes changes. This specifically ties into understanding climate extremes and changes in water balance in the western U.S., including the Great Plains region, and how these extremes affect ecosystem response. Other work includes future climate change uncertainty in the context of decision-making and climate adaptation with experience in development and communication of useful and usable future climate change scenarios for natural resource management. Dr. Rangwala also has expertise in climate change in high elevation regions. Please help me welcome both of our speakers.
Thank you. So am I ready to go?
Yes.
Okay, thank you. So this is Imtiaz Rangwala, and I'm happy to present this webinar with my good friend and collaborator, Gabriel Sinai. And we're going to talk about a tale of two products here, and both dealing with kind of drought detection and monitoring. And one specifically focused on the evaporative demand. I'm just trying to get to the arrow here. Yes. The evaporative demand term, and the tool is the EDDI tool, which I'll be talking about, and Gabriel will be talking about the evaporative response term, and the tool there is looking at the anomalies in actual evapotranspiration. So both these tools, and their value is, again, they're emerging tools, high resolution, near real time, they're very objective, so just based on algorithm and data that's fed in. And however, you know, they need some training for effective interpretation. So I'll go in, so for that interpretation, I'll just go into some physical concepts before I come back to the EDDI tool, and then Gabriel takes over and discusses his actual AET anomalies tool. If you just look at the land surface and we look at what are the loss processes for water on a land surface, and you see there is the component of groundwater recharge, or or loss to the groundwater, or runoff into streams, and then there's a loss to the atmosphere through this process called evapotranspiration, this combination of evaporation and transpiration. And in part, this evapotranspiration term is responding to what we call the evaporative demand of the atmosphere. So I'll spend some time talking about what do we mean by that and how do we measure this evaporative demand term. So effectively, evaporative demand is a measure of degree to which the atmosphere primarily is trying to evaporate water from the land surface. So it's often referred to as the thirst of the atmosphere, also as potential evapotranspiration in literature. And what I'll discuss today is more of this term called the reference evapotranspiration, used quite a bit in the agricultural systems. And that's the measure we use to kind of quantify the eddy tool. What's the relevance of evaporative demand to drought? And I just want to point out that although eddy and the tool that Gabriel helped develop has been primarily used or initially used in the agricultural system, we think it's quite applicable to the ecological system or the non-irrigated systems. So in a regional context, a sustained or emerging high evaporative demand could lead to water stress on the land surface. And that's where the relevance comes. So how do we measure it? And there are different ways. In the field, it's primarily measured or estimated through the span evaporation concept, and where you have this pan filled with water, and you basically, and the loss of water in the pan give you a measure of the atmospheric evaporative demand. So it's a very useful measure. However, there's a problem of adequate number of stations, observation stations out there. And then again, it's not responding as a crop would respond. It's just like an open water evaporation. So there are some limitations in that regards as well. But that's like one real physical measure out there in the field for evaporative demand. But primarily in the literature, you'll find that it's estimated using some kind of a mathematical model for potential evapotranspiration or reference evapotranspiration. And I've listed a few here, and they could be pretty complex to kind of more simpler forms. So one mathematical model is related to what we call evapotranspiration, estimating that term. And what that is you have a reference condition under which evaporation is happening, and you're measuring actual evaporation in the reference condition given a particular climate. So here, one that the FAO, the Food and Agriculture Organization, uses is a reference grass crop of a certain height. This is just under 10 centimeters here. And it's a well-watered system. And if you have a certain climatic condition, what is the evapotranspiration from that? And that's kind of the measure of the evaporative demand. The specific method we use for the eddy tool is to estimate a reference evapotranspiration is the Penman-Monteith method, and I would assume most of you would be pretty familiar with that method. And that method is pretty comprehensive in the sense that it's like it considers a whole suite or full suite of meteorological variables varying from temperature, wind, sunshine, or I would call net radiation and humidity. So and we are finding that this model, a fully physical model, captures, especially on very fine time scales, a lot of these processes and variability that some other models do not. And I'll show you some comparisons of that in the next slide. What you see here is the pan evaporation across the continental U.S., kind of the mean value of the evaporative demand from May through September compared to a Penman-Monteith based reference ET. And what you kind of see is that it kind of shows in the bulk part large similarities where you see high magnitudes of rapid demand in the southwest and the central plains region. You also see the trends in quite clearly the trends in high coefficient of variation across the Great Plains region. And again, it's kind of high interannual variability or year-to-year fluctuations in evaporative demand. And so kind of this method we've been finding through other work, other research work we have done comparing different methodologies to estimate ET0, that Penman Monteith is kind of a good measure for ET0. So yes, getting back to the tool itself to kind of understand drought risk at any particular point in time is the EDDI tool, the Evaporative Demand Drought Index, and what it shows is how anomalous the evaporative demand is at a particular place you're interested in relative to a historical period. And the historical period here is kind of the satellite era period for us. That's from 1979 to current. And so it's really looking at how anomalous the rapid demand is can give you a pretty interesting assessment of risk. And as you can see right now, there is high anomaly in ET0 in the southern part of the country, southeastern part of the country, and kind of this region of Kansas and Oklahoma, where we kind of have seen a lot of wildfires. So again, that wildfire is one, wildfire prediction is one kind of risk that EDDI is fairly pretty good at providing us information on. The other other stakeholders who are interested in EDDI at this point and could be relevant to are the dryland or irrigated agriculture, flash drought alert, or just folks who are interested in ecological impact in terms of growth and mortality of vegetation. So how is EDDI calculated? So for any region and a time window that you're interested in, that could be subseasonal to seasonal, you get these meteorological input at high resolution. For operationally, we use the 12-kilometer NLDAS product. There's also this 4-kilometer product that's out there for EDDI. And that meteorological input goes through this Penman Monteith formulation to calculate the reference ET term, and that is then taken through the standardization process because it uses a not rank-based non-parametric method that kind of furnishes the EDDI value. So let me say a little bit about what are some of the characteristics of attributes of EDDI. So we show EDDI as in these percentile categories. So the hot colors are showing drought stress, and the cool colors are showing kind of the lack of it. In fact, that could be used for some kind of a flood risk assessment. And these percentile categories are kind of similar to, or basically identical to the ones used in the US Drought Monitor. So that's one easy way to interpret it, and you can see that the white is a white margin where you have normal conditions. One thing that's really relevant to interpretation of EDDI and the risk and the drought risk that EDDI is kind of pointing to comes from the consideration of timescales. And so you can look at EDDI from weeks to months to kind of seasons to years, and I guess that's where the interpretation is quite salient. One of the particular strengths of eddy is to capture these precursor signals of water stress at weekly to monthly timescales. So if you're looking at those weekly to 1 month timescales, you're probably looking at emerging conditions of high evaporative demand or emerging risk of a dry atmosphere that from which stress on the land surface can build up. And if you're looking at much more long-term values of eddy, then it's something, what it's pointing to is the persistence of a particular condition, of a drought condition. So emergence versus persistence, that's kind of the two different ways to look at eddy. And, we constantly look at different time scales when we're using eddy to look at how the drought is emerging in a region or drought stress is emerging. Seasonality is another issue that's relevant. I mean, you can look at the maps in kind of the cold season and in the warm season, and you may have a different sense of concern. I guess I just lost my pointer. Okay. So as a general rule, one should be, as we are looking at and kind of learning more about eddies, that we're finding that as a general rule, we should be more concerned about short-term, especially the short-term changes in eddy during the warm season. Okay, so I'd like to take you through a couple examples where show how eddy could have provided useful information and an early warning. And this is basically looking at the short-term eddy and comparing it to the USDM and looking at, looking at the 2012 drought development in the Midwest region, so that's in this box here. And what you see is that that eddy was showing a development of this exceptional drought risk in the Midwest region pretty much 2 months ahead of when it appeared in the U.S. Drought Monitor. And so we see this lag where drought stress is kind of seen on the landscape and where the precursor signal from eddy starts showing up much earlier. And so that's kind of the early warning attribute of eddy. This is another example from the Wind River Indian Reservation where they had in 2015 growing season a miracle May rain event or episodes, and it was just a very wet period, and then suddenly the region felt a micro drought emergence during the rest of the warm season, but didn't show up in the USDM until very late. And when you look at the 2-week eddy plots here, it kind of shows kind of the nature of stress that was felt on the landscape, and kind of this was somewhat corroborated by the anecdotes from the stakeholders in the region. So again, another example showing this kind of the early warning capability of eddy. So what's the take home for eddy? It's a standardized drought index, works solely with the evaporative demand terms, so it's just telling us the atmospheric side of the story in terms of what stress the atmosphere can produce on the land surface. It's near real time, so the operational product is just 5 days behind at this point. High resolution, so we have 12 and 4 kilometer product. The work across multiple time scales, and so you can look at sub-seasonal to kind of multi-seasonal drought processes and understand how the whole risk is evolving over these time scales. And as I said earlier, it's just effective for early warning and monitoring. We have several resources for eddy, and I'm just showing the eddy 2-pager slide here, which we wrote in December 2015 and has been kind of widely, it's been pretty visible and widely read. But we also have a resource a list of resources at the end of the presentation that will show where you can see other resources. So at this point, I'll hand over to Gabriel to move to discussing the actual ET.
All right. Thank you, Imtiaz. So I will focus now on the actuality as opposed to the potentiality that Imtiaz discussed. The main difference is really, the potentiality is more a driver, and actually it would be the response of the landscape based on the availability of soil moisture. So if I use this, we'll have some brief background and some products, Drought Monitor versus ET anomaly comparison, and also I'll talk about the Missouri River water balance that uses actuality. So why ET? When I refer here ET, it's going to be the actuality as opposed to the potentiality. As I said earlier, it's a response variable as opposed to precipitation or potentiality. It reflects the integrated effect of energy and aerodynamics. That's pretty much the potentiality, but also includes soil moisture, vegetation condition, environmental stress. All the one you see on the right hand are the limitations. If you don't have soil moisture or the vegetation is not in good health, or there is like environmental stress like salinity, the vegetation, the landscape cannot evapotranspire. Even the demand is very high. So what you see on the left side is the potentiality. So on the left side, you see the energy and the wind relativity, which means a sunny day, and a drier atmosphere, and a windy atmosphere will have a higher, much higher potentiality. But that's based, conditioned upon soil moisture is available, vegetation in a good health condition, environmental stress are limited. What I'm going to talk about is how remote sensing is going to help us estimate these limitations. Actuality is, again, can be used for monitoring and assessment purposes, whereas potentiality is good for design purposes and planning purposes. So once we have actuality, we can monitor drought, we can monitor water resources, water resource conditions. How do we estimate actuality? There are two principles. One is the mass balance, or the water balance, and the other one is energy balance. Water, the evapotranspiration process, is a movement of water, which is mass, or it's also a transfer of energy from liquid to gas. So if you have good precipitation rainfall data, you can use a mass balance approach, or what you are measuring is really temperature difference, which is one way of expressing energy differences, and that you could use an energy balance approach. Where is remote sensing coming in? Remote sensing is a data source. So for land surface temperature, we use satellite data coming from Landsat, about 100-meter resolution, or MODIS, AVHR 1 kilometer, or if our interest is global, we use the geostationary satellites that gives you 10-kilometer data. Again, if you're doing a water balance approach, the most important information is getting precipitation information. For the US, we have daily data from NOAA NEXRAD at 5-kilometer resolution. For global data, we have like NASA TRIM at 25-kilometer, or a European satellite called Meteosat at 10-kilometer resolutions. So just by an example to show contrast and how complementary between potentiality and actuality, I'm showing you now just a one-year product, 2005 in Arizona. In the yellow line, what you see on top is the rainfall, and there is the green line, the potentiality. Somewhere around May, June, the potentiality in Arizona is high, as you would expect. Whereas the actuality is very low because moisture is not available. And then the monsoon season comes in July, August. As you can see, the potentiality and the actuality become very close because moisture is available to meet the demand, the atmospheric demand, which is the green line. So for a water balance approach, what we need is a precipitation data, source information, and some potentiality that MTS described, and some just water budget accounting on a daily time scale to know the soil moisture status. So that's pretty much a water balance approach, because evapotranspiration at the end is a function of soil moisture. Again, and then with that kind of water balance approach, we can obtain potentiality and also actuality. And the bottom, what you see is really modeled and observed with the flux tower. There is very good agreement in some of the methods we use. What are the limitations of water balance? Because most of the presentation is going to be on energy balance approach using satellite data. I just want to point out why we are not using a water balance as much, which means, well, we need to get good rainfall data, which is not a problem in the US and other parts of the world. Getting good rainfall data, gridded data is difficult. But more importantly, we don't know how much the farmers are applying. If that information is not there, we cannot really monitor irrigation water use through a water balance approach. We don't know how much they're applying. That's why an energy balance approach, which measures the temperature of the land, is a more practical approach. So a direct estimation of landscape stress can be measured using remote sensing thermal data. So from now on, I will be talking about how the temperature of the land surface is used to get actual ET. So when we do an energy balance approach, again, we're just pretty much monitoring the temperature change across the landscape. We are accounting for water stress, agronomic stress, and environmental stress. All the stresses are combined and expressed in changes in land surface temperature. This is an example of conus-wide in parts of Mexico, annual ET, actual ET, how much the landscape is evapotranspiring. As you would expect, in the southeastern US, where the energy demand, the potentiality is high, but also soil moisture or rainfall is high, you would expect a higher evapotranspiration. On the western US, on the other hand, actual ET is much lower. But if you see a potentiality map of this, actually the potentiality is much higher in the western US. But what's actually being responded by the landscape is much lower, except irrigated lands like the Central Valley areas. So the method we developed at the USGS EROS is a very simplified approach. It requires potentiality, again, to know the maximum demand of the atmosphere, but the limitations come from the land surface temperature. We use air temperature to parameterize it, and then we come up with an ET fraction that varies from 0 to 1. Pretty much we are scaling the potential ET. Yeah. So the equation can be simplified further, again, without going into the details. This actual ET is really, we're subtracting the fraction, you're just taking away the limitation from the potential ET. So if this item is pretty much 0, the actual ET will be the same as the potential ET. So the limitation is expressed by the difference between the land surface temperature, which is the skin temperature, as compared to the air temperature. So when the difference is close to 0, which means there is no sensible heat transfer, all the energy transfer is in the form of latent heat, which is evaporative cooling. That makes this term pretty much 0, which means our actuality is comparable to the potential ET. The data, satellites provides this data, and this comes from meteorological data. So that's the most important information, is really the difference between land surface temperature and air temperature. Just one more slide on, and then I'll show examples how the difference between how important land surface temperature is, how dynamic it is. I'm showing you now transect from the mountains of New Mexico all the way to part of Oklahoma, Arkansas. So the mountains are in here, on the west side and the plains in the east. What you see in the middle is the land surface temperature by MODIS for a given day, July 4, 2012. As you can see in here, as you go into the mountain, the land surface temperature dips. As we know, as you go into the mountain, it becomes cooler. And then it rises up. And as you can see, it goes up and down and up and down. Now, a comparison with an air temperature, as you'd expect, air temperature is also cooler in the mountain, but air temperature changes very, very slowly. That's why we call it kind of a regional variable. It does not vary at a local scale. Whereas land surface temperature varies very highly because the local variable, it depends also soil moisture and evaporative cooling. So the data, this is a repeat, the data comes from land surface temperature comes from satellite, Landsat or MODIS. Air temperature for motor parameterization comes from different sources. And the potentiality comes from GDAS, NLDAS, GridMate that Imtiaz talked about. Satellite data, so a lot of you may be familiar with. We have from MODIS, we have almost twice a day data, land surface temperature at 1 kilometer for the whole world. And MODIS has got, for example, 36 bands, and two of them are in the thermal in the east and the right side of the graph, and those are converted to land surface temperature by NASA, and this is freely available for anybody in the world. An example of a land surface temperature map is shown in here, just an 8-day average for the globe. And as you would expect, the Sahara is warmer, that's where soil moisture is not available. And potentiality, solution of the Penman-Montes equation, we also produce this at arrows for the globe, but for the US, there are better data sources. But this data, again, are freely available for anybody. So we use, again, as I said earlier, Actuality is a monitoring product. So we monitor the landscape. This would be being absolute magnitude. What I'm going to show you is actually anomaly, so a deviation from a median. So this is, for example, for the growing season in 2015, from April to October. As you see, greener colors are above normal condition when rainfall is much available, so ET is much higher for that period, whereas brown colors are below normal condition, which means drier conditions. That's 2015. Now I'm going to show you more years. That would have been 2014, again in California and northwestern US, a dry condition, but also Texas 2014. I'm going to show you now more years. 2011, the drought in, if you remember, Texas, Oklahoma, and 2012, that Imtiaz also showed widespread drought in much of the US. 2013 again, so repeat drought in this part of the US. And you can look at also, you can go back to 2000, that's the start of the MODIS satellite era, and noticeable drought years are 2002 and also 2006, much of the high plains. So this just demonstrates that the satellite-based data is really helpful in capturing drought conditions at 1 kilometer scale. How does this compare to also Drought Monitor? So that's just a few slides on comparison with Drought Monitor. This is, for example, from previous year, 2016. This is, there's a time scale issue as Imtiaz showed. This is a seasonal product, what you see on the right. See, this is a seasonal value, and the Drought Monitor is just a weekly product for August 16. There is generally a match in different slots, but it's not exact. But if you look at 1 month like July, the intensity would be here. So you have to, what we do is just we try to find different ways to compare the two products one to one. This is a more current product. So what is shown here is from our global ET anomaly product. It's hard to see. Generally, much of the world is really doing well. This is from October to March. This is mainly a growing season for the southern hemisphere, but generally the weather condition for the world, as you come to the US, It shows dryness in the southeast, and also even part of the central plains in here, especially eastern Colorado as well. So how does it compare to a weekly product of Drought Monitor? As you can see in here, there are also some decent comparison in southeastern U.S., also central U.S. Again, there is a difference in time periods. So what we try to do is, okay, well, how about if we aggregate the Drought Monitor, and then there will be a more comparable temporal match. So I'm going to show you that on the following few slides. For example, on the part of the North Central Climate Science Center study with Dennis Ojima and Bob Flynn that did this work. So this is our product from April to October, drought anomaly from actual ET. We aggregated the Drought Monitor from June, July, August, and you can see a very good comparison when we are looking at comparable time periods. Now I'm going to show you another year. So this will be 2012. So a widespread drought anomaly report from Drought Monitor, and the same from just automated processing of remote sensing. And this would be 2013. Again, Drought Monitor doesn't show you when it's above normal condition, but the ET anomaly from remote sensing, the green shows you above normal condition. But generally, it's a very good match in here. And this is 2014 again. As you can see, the epicenter of the drought here in the center, and comparable depictions in here. Again, the advantage of this is a 1 kilometer resolution. Just there is a lot more detail. So I'm just going to show you now how does this also help us understand water budget conditions and river basins and stream flows. Well, one way of looking at it is, well, we have to combine ET with other supplies like precipitation and runoff. So runoff being a driver, precipitation being a driver, this is the whole Missouri River Basin. This is a relatively new product. It's just a preliminary result I'm showing you. As you would expect, there is higher precipitation towards the mouth of the Missouri River, and lower precipitation in the headwaters. As you can see, there is a general gradient in here. And how does this look from ET point of view? This would be the response of the landscape as a result of this precipitation. So this precipitation comes in here. This, what you see in here, is how the landscape used the water. If it is not used in the form of ET, it's probably runoff, or it recharges the groundwater. So as you would expect, higher rainfall areas, give, denser vegetation and more evapotranspiration, but much lower ET over here. But the difference between the ET and the precipitation here, there is a lot more fine detail in here, because there is a higher spatial dynamics in vegetation as compared to rainfall, at least at annual time scale. When you convert this ET in terms of anomaly compared to the median year, then it will show you pretty much what I showed you for the US, but this is for the basin. So a lot of drought years in the 2000s, peak drought in 2002 for the basin, another major drought in 2006, but generally drought years from 2000 to 2007, more recent years, and then from 2009 on, really the drought appears to be just disappearing. No drought 2009, 2011, and then of course 2012 came, and then really wetter period until 2015 as well. So this remotely sensed driver data really help us understand, also look back in history, 2000 with motors. If we go to Landsat, we can go back to 1980s. Just this slide, just to finish it off, just what I showed you earlier. If we look at the water budget, what's in here is just year by year, the three important water budget components, precipitation in blue, and the ET, and what's remaining is runoff. So an ideal condition, generally at annual time scale, the three of them, they add up to 0, because this is the driver. Precipitation is being split into ET and runoff. And as you see, precipitation being important, the drought years, I just highlighted them, and here they show up. Precipitation is lower, as you would expect, ET will be lower, and also runoff will be lower. And what you see on the lower right graph is the seasonal dynamics and month-by-month variability of the different components. Precipitation comes in, the peak precipitation happens by June, whereas the peak ET occurs in July, where energy demand is high in July, but also vegetation is also more dense. But having a remote sensing derived value like this will help us understand water budget distributions. I think our time is running short, so I'll hand over now. This is pretty much the summary of what I said. I think the full MTS has got a few more concluding slides.
Thank you, Gabriel. So I'll just conclude with a few more slides, primarily talking about the two terms that we kind of walked through today, and I collaborate with Gabriel on kind of integrating these two data sets in a way that could bring about more robustness to our understanding of drought mechanism and a more robust monitoring as well. So Gabriel mentioned the complementary relationship between potential ET and actual ET, and so kind of looking at the conditions of these two terms and exploring here the processes of drought development and dissipation. And so it is kind of a conceptual framework, and then we like to look at the real data and see how it behaves in different parts of the country. One way you can actually do right away is look at these both EDDI and the actual AET anomaly tool, and compare the different timescales and explore how in different regions droughts persisting or emerging, or just the kind of state of where the drought stress, what kind of drought stress there is. So, for example, here, if you this is an example from July 2016. There was a high eddy in the Texas-New Mexico region, and there's also a low actual AET anomaly, and that kind of tells you about that. This is really there's some severe drought stress out there, and it's likely to persist. Whereas if you can look at another location here, somewhere in the Mid-Atlantic, you kind of see that the conditions are, the AET is kind of near normal or slightly above normal, but there's an emerging evaporative demand, and so kind of we can keep an eye for a drought emergence in that region. So just kind of a couple examples of how we've been looking at these processes on these products, and exploring how to kind of bring together these two information at high resolution to get a just much more robust understanding of drought mechanisms. So as we go into Q&A, I'll leave you all with this slide on resources, and there are many more of these out there and in process of development. So thank you for your attention.
Excellent. Thank you so much.
Hi, Ashley. This is Robin O'Malley. Can you hear me?
Yes, I can. Hi, Robin.
Hi. Can I ask a question?
Please.
Great. So this is a question for Imtiaz, and I'm interested in the sort of projection and prediction possibilities here. And you showed a couple cases where you showed an eddy set of observations, and then later on you showed the drought monitor, and obviously there's an early warning component to that. Have you looked at that enough to be able to say at any point, if eddy is here and conditions don't improve, the drought monitor will end up in a 4 or a 5? So, if it keeps going down and things stay bad, here's where it will bottom out. Or if we get rain, it may only end up. So the sort of shape of the evolution curve, could you start to get a sense of how deep a drought will be if it continues? Is that a possibility?
Yeah, thanks, Robin. That's a great question. In fact, yeah, the developers of eddy and that are based at NOAA and the Desert Research Institute actually have a paper out there in terms of forecasting eddy, where they see there's probably more skilled in forecasting precipitation on a subseasonal time scale, because variables like temperature and radiation and others may be a little more skillful for forecasting at those time scales. So yes, so that product is not operational right now. It's still in the experimental phase. It's been done, and I think it would be interesting to see what kind of skill it has in doing that. But that's very much in the pipeline, so right thinking there.
Yeah, great. Thanks.
Thanks, Robin. Are there any additional questions? And I apologize, but my Adobe Connect has lost connectivity, so if you're typing into the chat box, I cannot see it at the moment.
Oh, okay, I can see it. The question by Dominique is, can you relate change in ET to changes in vegetation cover with any precision, like in desert? Okay, so I think, Gabriel, would you like to take that?
Sure. Yes, ET is a function of, of course, the potential atmospheric demand, but also the vegetation composition type, stage, and also soil moisture. So different vegetation types, whether because of their structure or their just water use, they will reflect differently. So it should show. The good thing is we don't need to know the vegetation type to model its ET, but you can use vegetation cover to understand, how much different vegetation covers are responding. So yes, different vegetation covers should show. But if it is small, patchy kind of area, we have to use a higher resolution data like Landsat or even smaller. But if you are interested in basin scale, modest 1 kilometer. So really the challenge is, do we have the spatial resolution from a satellite? But in terms of really different vegetation showing different ET response, that happens. I don't know if...
And our question was, I guess, follow-up was, can we detect invasives in deserts if we have a high flux of precip?
Yeah, again, so the quality of the data we're getting is the same thing in the deserts and shrublands as well. If it is a small amount of ET, like really high desert areas, then our accuracy will be working close to the margin of the error. So that depends on them getting really a higher quality remote sensing data, higher spatial resolution, and more frequent data. But the response will be captured. The response will be captured if you have the data.
Excellent, thank you.
So I see another question out there typed by Ryan for use of eddy and how sensitive eddy is to underlying reference vegetation. So I think that's a good question there. I mean, because eddy is calculated using reference evapotranspiration, and reference really is reference condition. These are reference crops. And so what's the applicability to, other places? I guess that's where I think this question is going. And so eddy is really kind of looking at the anomalies. And so if it was really looking at absolute values of reference evapotranspiration, that would be an issue. But we feel that the anomalies really work with the atmospheric side of the story, although, as we're working with gridded temperature and humidity data that are controlled by land surface moisture conditions, but primarily it's the atmospheric side of the story. So the reference vegetation in the context of eddy do not matter that much to the kind of information it's providing.
Excellent, thank you.